Alright, so for today's problem we have a square with a triangle inside of it, and we want to find the perimeter of it. And so the way we're going to do this is we have all these different values for the legs of the triangles and the outside edges. So we're going to find the lengths of the edges, and we're going to work inwards to find the sides of the triangle. So the way we do this is we have all these triangles on the outside, and we know that 8 is on one side and we have 2 on the other. So since they're the same, we can just subtract to get 6, and 4 plus 4 is 8. So we can find the lengths of the other sides. And now we can find hypotenuses. So to find this, we have the Pythagorean theorem, a squared plus b squared equals c squared. And at this point, we're just substituting our values for the legs of our triangles, our a's and b's, to get our c values, which is the edges of the triangles on the inside of the square. And this is what we need to find a perimeter. So 6 squared plus 8 squared equals 10 squared. And we just repeat this with the other triangles. Remember, putting the a squareds and the b squared, putting the a and the b in the formula. And we get 2 square root of 5 as c, and 4 square root of 5 as the other c, as the other hypotenuse, rather. And so, basically, we can just add these together now. 10 plus 2 square root of 5 plus 4 square root of 5, which amounts to 10 plus 6 square root of 5. And that's the exact value. That's our simplest radical form. That's going to be our answer. But they also want us to find an expression, even though we already found the perimeter. So the way we're going to do this is we're going to backtrack, and we're going to just write our Pythagorean theorem again, and then put a square root on top. And so we're just going to do this with each triangle on the outside of the triangle on the inside. So we have that triangle on the edge, 6 squared plus 8 squared, with a square root on top, because a squared plus b squared is equal to c squared. So if we put a square root of c squared, yeah, so that's just pretty much it. It's not hard. We just rewrite and backtrack, and then we have our expression. And now our next problem is a bit tougher. It's about an ant absorbing oxygen at 6.2 milliliters per second for each square centimeter of its exoskeleton. So basically, this is how much air it can take in through its outside. And then 24 milliliters is the amount of air it needs in the inside. So like if you're breathing, it's the amount of air you can get through your mouth and the amount of air you need. So our question is the ants. So we want to assume that it's cylindrical, is what they're saying, and then we have all these measurements we have to test, and then we have a writing question, which you're just going to ignore for now. We'll get back to that later. So what matters is the ratio, because we want to figure out if the ant can live or die with the measurements we have. And so the first one is going to be surface area, because it's the outside, the exoskeleton. And the second one is going to be, the second measurement is volume, because it's the inside. And then we want to find the ratio, because if an ant can't take in enough oxygen, if it doesn't have the surface area to take in enough oxygen to support its inside, to support everything on the inside, its volume, it's going to die. And so we're just going to compare these. If the surface area is larger than the volume, or the same as the volume, it should be able to sustain itself and live. But if the volume is larger, then it will die. So this is what we're going to figure out. This is what we're looking for as we head into the problem and make our calculations. So for question A, we want 10 millimeters and 2 millimeters as the radius. 10 millimeters is the height. So we just substitute. We have the formula from the previous page, and we just substitute our values in. We find our surface area is 48 pi. And then for volume, we do the same thing. We substitute. It's pi r squared times the height, and we just substitute everything in, and we find that it's 40 pi. And so the surface area is actually larger than the volume, so the ant will not die. And this makes sense because the ant's small, right? So this is the usual size of an ant. It's usually around this size. But now we have the next one, except it's not millimeters, it's meters. So we have to convert it to millimeters, because everything in the previous problem and all the measurements is based on millimeters or milliliters. So we know that meters are just, I did that conversion before. Meters are just 1,000 millimeters. So we replace everything with 2,000 and 10,000 instead. we get 40 billion for the volume, which is a large number. As you can see, I had pretty trouble calculating with all those zeros. And then for surface area, we just substitute again, except we get 48 million as opposed to 48 billion. And that's because we're not multiplying everything by each other, we're also adding things together. So it amounts to less. And so the surface area is less than the volume. The volume's larger, so the ant died, unfortunately. But that makes sense because you don't have ants that are 10 meters tall. That's just crazy. That's taller than a human being. Much taller. So question C just wants us to elaborate on our answer, and it just wants us to prove that giant ants don't exist. And this makes sense because the volume increases exponentially, while surface area increases like slowly. So the larger you get, the harder it becomes to sustain yourself by breathing, because you can't take in that much air. So that's basically why ants aren't that big, I guess, if that makes any sense.